Good evening, Dr. Werner. I'm doing my presentation on polydentate ligands, specifically the synthesis and spectral investigations of manganese 2, cobalt 2, nickel 2, copper 2, and zinc 2 complexes of a new polydentate ligand containing a 1,8-naphthyridine moiety. With some overview, metal complexes with organic ligands are biologically important because of their ability to sequester heavy metals in regards to heavy metal poisoning, as well as a number of other things. So they have a lot of importance in medicinal chemistry. Polydentate ligands in particular also are more effective at forming these metal complexes than the lesser chelated ligands of the same donor atoms, which is similar to ethylene diamine in comparison to just amine. And then also 1,8-naphthyridines in particular are a group of biodynamic agents whose coordination chemistry was not well studied, at least in 2006, which is when this paper was done. They are also typically bridging ligands, using these two ring nitrogens as their donor atoms. So now looking at this paper specifically, the Swami group looked at the chelating properties of 3 different substituted 1,8-naphthyridines. The first one, as seen over here, was 2,O-hydroxyphenyl 1,8-naphthyridine, now known as HN. The second one, which is over here, was 2,4-hydroxy 6-methylpyran 2,1,3-il 1,8-naphthyridine, now known as HMPN. And then the third one, which is over here on the right, was 2-benzimidazole 2-il 1,8-naphthyridine, now known as BN. And they looked at the complexes they formed with 5 different metals, being manganese 2, cobalt 2, nickel 2, copper 2, and zinc 2. So the first thing they found was that all complexes that were formed were non-hygroscopic and that they were also stable at room temperature. And in regards to the complexes formed with the HN and HMPN ligands, which when referring to both of them, you can just refer to them as L, they were only soluble in DMSO and DMF reagents. And so they used DMF as their solvent, as seen over here. And because of the fact that they had a small molar conductance value, it meant that these complexes were non-ionic. And now in regards to the BN ligand, they were insoluble in all common solvents, therefore the molar conductance couldn't be calculated. And for all the complexes formed, all 15 of them, they had a large insolubility, which indicated that the complexes that were formed were neutral. Next, they looked at the mass spectra, and when looking at the mass spectra for just the ligands, they found that the highest mass peak and mass to charge ratio for HN was at 223, HMPN was 254, and BN was 246. Please note that for HMPN in the literature they said 254. However, in the table it says 258. I don't know if that was a typo or if it has to do with something else. But then next they looked at the mass spec of the complexes. And they found that the most notable fragments in all of the complexes pertained to these two ionic compounds, where it was the metal complex, but with a +1 charge. They also noted that there was a presence of these smaller fragments, where it didn't have either the water or the acetate ligands that were bound to it. And because of the fact that these smaller fragments existed, they confirmed that there was a metal-ligand interaction, and then thus confirming that these are the general formulas for each of the ligands, where M is any of these 5 metals that are listed above. They then looked at thermograms for HN and HMPN, and they found that they had a weight loss in 2 different temperature regions. A lower one at 150 to 250, which exhibited an exothermic peak, as seen over here, which indicated the loss of 2 water molecules that were bound to the metal ion, and then a larger temperature region, which was between 260 and 800 degrees Celsius, which had to do with an exothermic peak, which kind of looks like this, which had to do with the loss of organic matter, which for HN and HMPN was just the organic ligands, and what was left were metal oxides. Please note that this figure was not part of this paper. It's just here to show a reference to look at what an endothermic and an exothermic peak looks like. They also confirmed that the formulas for HN and HMPN are as such, and that they're also both bidentate ligands that have a -1 charge, and that they form octahedral coordination with the 5 metal complexes. The thermal analysis for BN revealed something slightly different. It only showed a weight loss in one thermal region, and that was between 208 and 800 degrees Celsius, and that was because this was the decomposition of the organic compounds in it. And they associated that with 2 acetate ions and 2 BN ligands. They looked at the experimental data and the theoretical data, because they looked at some literature, were in agreement. Therefore, they confirmed that this was the formula for BN, like the general formula for BN. They also identified that it was a bidentate ligand that had no charge, so it was neutral, and that it formed an octahedral coordination with the 5 metals that were looked at. Looked at the IR spectra for the HN and HMPN ligands, and for the IRs for the ligands themselves, they noted three important peaks, running about 1600 wave numbers for the C double bonded N, one at around 3400 for the hydroxyl peak, and one at around 1200 for C single bonded to O. And then in regards to the IR for the HN and HMPN complexes that were formed, they saw a fat hydroxyl peak between 3100 and 3600 wave numbers, which was likely associated with the water molecules that were part of the complex. And then there was a new peak at around 800 that further confirmed that those waters were coordinated with the metals, with the metal ions. In regards to the C double bonded N and the C single bonded O peaks, they were both shifted down between 10 and 30 wave numbers, which also confirmed that these organic ligands were coordinated with the metal ions themselves, or also, but in particular with the ring nitrogen and the phenolic oxygen atoms on these organic ligands. We then looked at the IR spectra for the BN ligand and noted that the only real notable peak was at around 1580 for the C double bonded N. They also looked at the peaks for the acetate ions and saw that they had 2 different peaks for the asymmetrical and the symmetrical free ions. When they looked at the IR for the BN complexes, they saw that the C double bonded N peak was shifted down a little, which confirmed that the BN ligand was in coordination with the metals via the nitrogen on the naphthyridine and the nitrogen on the benzimidazole groups. They also saw a slight shift down in wave numbers for the acetate ions when they were in complex. But more importantly, the differences between these new peaks for the acetate ions in complex was greater than 144 wave numbers, which meant that acetate was actually monodentate within these complexes. Then there were 2 new peaks that were just associated with the metal binding to the donor atoms on the ligands. They then looked at the HNMR spectra, and they looked at all the protons, but the only really important proton to note was in HN and HMPN ligands. It was the phenolic hydrogen. That's because of the fact that it had a peak at these 2 ppms. And when they looked at the HNMR for the zinc complexes with these 2 ligands, these peaks disappeared, thus suggesting that there was deprotonation of those phenolic hydrogens, which would then suggest that the oxygen that those hydrogens got deprotonated from bound to the metal, forming these complexes. They also noted that when in the NMR spectra for the zinc ligand complex, that there was a new peak at 5.55 ppm, and that had to do with these water molecules that were coordinating with the metal. And because of the fact that BN complexes were insoluble in like the common solvents that they looked at, they couldn't get an NMR spectra for it. Looking at the magnetic moment, they found that manganese 2, cobalt 2, and nickel 2 complexes were all in their high spin octahedral they all had a high spin octahedral complexes, which meant that those electrons went to the highest unoccupied orbitals before pairing up in the lower energy occupied orbitals. They found that manganese 2 had 5 electronic transitions, and cobalt 2 and nickel 2 had 3 electronic transitions, all 3 from the ground to the excited state. And the beta value they determined was less than 1, which meant that the metal ligand bonds were covalent. They also found that copper 2 complexes only had 1 electronic transition, and it was associated with a distorted octahedral geometry. And because of the fact that zinc 2 is diamagnetic, means that it has no unpaired electrons in its valence shell, it couldn't do any DD transitions. Therefore, they used UV vis, and they noted that there was a shift from just the ligands to when the complexes was formed, which suggested that the ligands bound to the metal, to the zinc. Looking at the conclusions, they determined that all 3 of the ligands were bidentate, while BN was neutral and the other 2 ligands had a charge of -1. They also, all three of them formed octahedral complexes with the 5 metals that were looked at. And for HN and HMPN, the donor atoms was the phenolic oxygen, as seen over here and over here, as well as the ring nitrogen, as seen over here and over here. Meanwhile, for the BN, the donor atoms was the N, the naphthyridine, as well as the N in the benzimidazole group, as seen over here and over here. And the general formulas was a metal bound with 2 of the organic ligand, and then 2 waters for HN and HMPN, or 2 acetates for BN. And then they also determined that because of the fact that they had this electron pair donating atoms on these phenol rings, it pushed basically these other nitrogens further away, preventing them from forming bridging ligands, which meant that all the complexes that were formed were mononuclear. Over here, I just added in some experimental procedures, just so you can read it, but it's not super important to go into, and then also how they prepared their complexes. And then these are my references. This is for the paper, and then these ones are for the images that I used. Thank you.